All right, screen is shared, recording is going. I think we're ready to go. Any questions before we get started? All right, I'm not hearing anything. Here's where we left off. If you let me back up a few slides, we were talking about type def. And I introduced it as a way of giving a short name to an arbitrarily complicated type. And we talked about a few different ways of using it. You can make your code more portable. You can shorten your code and make it maybe more readable by coming up with short names for longer, complicated types. I was about to make the point that this is one reason it's kind of handy that you can make a struct that doesn't have a name. Earlier when we were talking about the syntax for structs, I showed something that looked like this. So just ignore the type def for a moment. You can define a struct as struct and then leave out the name part and then define all of its fields. And that's fine as long as you're going to go ahead and make an instance of that struct. Well, here, if we didn't have the word type def, event would be a new instance of that struct. But otherwise, we don't have a name for that struct because we didn't bother to give it a name. With the word type def here, just like any other use of type def, it means I don't want to make a variable. I want to define a type name that means whatever type that variable would have had. So this is often used to name a struct with a short name, one that you don't have to use the struct keyword with every time you want to name it. This has the disadvantage that the word event doesn't go into scope until the very end. So inside the struct, you couldn't really use the word event yet because it hasn't been defined yet. But if you don't need that, sorry, this works fine as a way to give a short name for a struct where you don't have to use the struct keyword every time, because you've already said, whenever I say event, I mean this particular struct. Type def, one more thing to say about type def, and that is it doesn't really create new types. It just gives new names for existing types. And the compiler knows this. If you've got multiple names for the same type, I guess in contrast, let's say you defined two different structs, but they contained exactly the same fields with exactly the same names. The compiler wouldn't treat those as if they were equivalent. Just like in Java, if you had two classes that had exactly the same stuff in them, Java wouldn't let you treat them as if they're the same thing because they're different classes, they just happen to have the same stuff. Same with structs in C. But if you use type def to just give a struct a different name, the compiler knows that that's just a different name for the same thing. And that's what I'm showing off here. I make a struct and its name is event struct, but I also type def that to just the name event. So now I've got two different ways of creating the same struct. The long way, I can say, make me a struct of that event struct type and put this stuff in it. I can say, oh, use the event type I just defined and put this stuff in it. The compiler knows these are secretly two different names for the same struct, and it'll let me assign between them. If they were completely different structs, it wouldn't let me do that. Sorry for the cough. This gets us caught up with where we were at the end of talking about structs. Questions before we move on to today's material? All right, now we're going to talk about what we can do with structs, or I guess a thing that we've been waiting to do for a while, and that is build data structures. Until we learned about structs, arrays were really our biggest way of making a data structure. And you can do a lot of fancy things with arrays, but without being able to build linked structures, there are a lot of things you can't do. Structs are going to give us an easy way of building what people would call linked structures. What's a linked structure? Well, you already know what this is. You've done this in Java. Maybe it wasn't called a linked structure, but when you build something like a linked list, that is a simple example, probably the simplest example of a linked structure. A linked structure is one where data is organized into one or more objects or nodes, and you keep up with more than one data item by having pointers or references between those objects or nodes. And that's exactly what a linked list does, as sort of our simplest example of a linked structure. Every node holds a value, and every node holds a reference or a pointer to some other node. And you can keep as many values as you want just by having a chain of pointers from the node containing one value to the next node containing a different value until you get to the end. And typically you'll use, I guess in Java, you would use a null reference to mark when you've hit a pointer that doesn't point to anything. We'll do the same trick in C. We've got a null in C, really a zero value for a pointer. It's written as capital null in C, but it's used about the same way as lowercase null in Java. It's used to give a pointer a value that means this doesn't point to anything. So we'll build a linked structure like this. It'll be our first example. Before we talk about that, let's talk about a few trade-offs, because like I said, until we learned how to make structs, we didn't really have a good way of building linked structures. We would have had to do everything with arrays. And arrays have a lot of advantages. In arrays, elements are stored one after another in memory, all in one big block. And that can be a really efficient way of accessing data items. I'm really talking about the frowny faces here, because when I made this slide, the smiley faces are the things that are good for linked structures. And I started by talking about, well, what's good for the way we've done things up until now? What's good for arrays? They're a bunch of items, one after another in memory, so they usually exhibit good locality. Your cache, for instance, is going to help a lot with performance if all your stuff is nearby in memory. And when you want to find a particular item, you can go straight to that item as long as you know its index. Linked structures have a lot of advantages, but cache performance is not usually one of them. To get around a linked structure, you may have to jump around between something stored in one place in memory and the next item stored maybe somewhere completely different in memory. It's nice to be able to jump around memory like that, but it's going to hurt your cache performance. What else is good about linked structures? Well, compared to an array, where you need a big chunk of memory all contiguous, all in one place in memory. In linked structures, you usually just need a little bit of memory here and a little bit of memory there and a little bit of memory somewhere else. So that can be easier to allocate a bunch of little pieces of memory rather than one big piece of memory. It's usually cheaper to grow it a little bit at a time, say by adding nodes to a linked structure. And we have figured out some awfully clever ways of organizing data structures if you let me use links or pointers between values. And I've listed some of them here. You probably know from your data structures class, things like balanced binary trees or disjoint set representations or linked lists or doubly linked lists, and a bunch of other things too numerous to name. So there's some advantages and disadvantages of both of these techniques. As a programmer, we can pick the data structure, we can pick the representation that gives us the best storage or performance advantages for whatever we're trying to do. But until today, we didn't really have a good way of building linked structures. Now we do. We're going to build them out of we're going to build nodes out of structs. And we're going to use pointers to represent the links between nodes. We'll start with a implementation of probably the linked structure that you got to see first as a software developer, a linked list. We're going to build a linked list in C, and here I'm showing the type we're going to use. So we'll make a node for our linked list as a struct. There's the definition of it. I'm calling it node struct. It's got an integer value in it, and it's got a pointer to the next node. So if you back up a couple of slides, I'm building something that kind of looks like this in memory. Value each node holds, and a pointer to the next node. Like we usually do, I called my next pointer next. That'll make it easy to remember. I said a moment ago, I picked kind of a ugly name for my struct, node struct. But that's because I'm almost never going to use that name. The next thing I do is I type def that to the shorter name node. Now, when it's time to talk about a node or to make one, I can just make an object of type node, and that means the struct I just defined above. I go ahead and make a head pointer from my list. Here, let's pretend that's a global variable, maybe. I just declared it as a pointer to a node. And I started it out with a value of null. And like you normally would for a linked list, that's a flag, or that's an indication that the list is initially empty. There's not even a first node on it. Just like you probably did in Java, I'm going to build this linked list by linking a bunch of nodes together. And I'll make head point to the first one of those. Here, I don't have any nodes yet, so head starts out at null. Questions before we try to put some nodes on this list? What's it take to put a node on a list? Well, I've got to get some memory for storing that node. And typically, that's going to be dynamically allocated memory. Like it says at the bottom of the slide, you wouldn't have to do it that way. If you allocate nodes on the stack as local variables, then the problem is they're going to go away as soon as the function that declared them returns. So that's usually a bad place to put a node. You could statically allocate them. You could make a global variable that had room for thousands of nodes, and then you could just use those over and over again. But with that, you may not know how many nodes you're going to need in advance. The nice thing about dynamically allocated memory is you can just call malloc whenever you need space for a new node. And then you can call free when you know that you're done with that node, when you remove it from your list. So that's what I'm doing here. I call malloc. So sorry, I should have said this little block of code is for creating a new node, linking into the list, and storing a value in it. So the first thing I do is I go to malloc and say, I need enough space for a node. Sizeof makes that really easy. However big a node is, I want that many bytes of memory. I cast, so that I get a void pointer from malloc when I call it like this. I turn that, or I tell the compiler, pretend that's a pointer to a node, and I store it in a temporary variable n, or a temporary variable n that's a node pointer. And then using n, I can use that memory as if it's an instance of a node struct. If I want to put something in its value field, n arrow value lets me store something in the value of the node I just malloced up here. So we're pretending variable val has the value you want to store in the node. Then we just have to link it into the list. The first thing I do is, well, maybe there was something already on my list. Backing up a slide, I'm assuming I've got this head pointer, and it points to the first node of my list. I just want to put another node on my list, and I'll make it easy for myself by putting that new node at the front. So maybe there was already something on my list. If so, I want it to come after the node I just made. So I make the next pointer out of the node I just made, point to whatever the first node on the list used to be. If that was null, then there's nothing that comes after the node I just made. But if there were already 100 nodes on the list, then the first of those 100 nodes is going to come right after the node I just made. So now what used to be the first node on the list comes after the node I just made. And the last statement here makes the node that I just created the new first node on the list. Head pointer now gets a copy of n, or said differently, now head points to the same node I just made, same node as n. Questions before we move on? So this is what it takes. So I claim we now know how to make a node, how to define it as an instance of a struct, how to dynamically allocate space for it, and how to put it at the front of the list, of a linked list. Like I said a moment ago, questions before I try to move on?
Oh, yes. So
Yeah.
this line right here with n dash next head, will
Mhm.
that alter anything about the value of the node? Like when you do that and then you assign it again, will it still like change the value of the node?
It shouldn't. So when you say the value of the node, you mean, for instance, node n, the one I just made?
Yeah, like you created node n and you linked its next node to be the head node, right?
This line, the second to last line here, the one I'm pointing at, I guess the way I would say that is whatever used to be the head node is now the node that comes after the one I just made.
Oh, okay. That makes sense. Thank you.
Yeah, in Java would be the same. You'd write the same code in Java, except these arrows would be dots. Because, and I've probably said this already, because what Java calls a reference is secretly almost the same thing as what C calls a pointer. Other questions? All right, so if we wanted to add a bunch of nodes to a list, we just have to do this for each node, 4 lines of code for each node we want to add to the list. Once we've built a big list, if we just want to print out or at least look at every value on the list, what would it take? Well, we normally call that traversing a list. And this is typical code for doing that. Here I'm using the trick that a null pointer evaluates to false and any non-null pointer evaluates to true. So I'm using n, it's the same name as the previous example, but here it's just a local variable that could be pointing to any node. N is my loop control variable. I started out with a copy of the head pointer. So you can think of when I first do this assignment, n is pointing to the first node on the list. As long as that node is non-null, or I guess said better, as long as I am pointing to a node, as long as n isn't a null pointer, then I must be looking at a node. So I'm going to print out its value. And this is what I started to say a moment ago. Here I'm using the fact that a null pointer evaluates to false. Any other pointer evaluates to true. So this loop will keep running as long as n is non-null, or said differently, as long as n points to a node. Here I just print out its value with a space after it. N is pointing to a node, so I can just say n arrow value to get the value field out of that node. I print that out. After I've printed out a value, I move to the next node. So this is saying take n, go get what's in its next field, and copy that, and now make n have a copy of that. Now make n point to the node that came after the one you were just looking at. And then when I print all these on one line. When I'm finally done, I print out a new line. So this is typical code for traversing a linked list. It's fairly straightforward. It's got a little bit of pointer syntax, but when you've got a pointer to a struct, that syntax is pretty easy to use because we learned it last time, this arrow operator for getting to any field of a struct, as long as we got a pointer to that struct. Backing up a slide, I said, well, all we have to do are these 4 lines of code whenever we want to put a new node at the front of the list. And that's okay, but I wouldn't really want to copy these 4 lines all over the place if I wanted to be able to easily insert a node or put a new value at the front of my list. It'd be nice to wrap this up in a function. So moving ahead, this is what we just looked at. This is our new slide. Let's wrap this up in a function so we can just call this function whenever I want to put a new node on the list. We'll assume I've got a global variable for the head pointer. So this is pointing to the start of my list. And then this code, I think it's exactly the same as the code we were just looking at. It's just wrapped up in a function. You call add value, you give it a integer value you want to put on the list. We malloc space for the new node, n is a pointer to that. We use n to fill in the value field of the struct it points to, and then we link it into the front of the list. I'll say this again real fast. Whatever used to be the first node on the list, now that's the next node after the one we just made. And head now points to the node we just made. Head gets a copy of the n pointer we were just using. Questions so far? So we're kind of trying to sneak up on making reusable code for working with a linked list. And this code is okay. A disadvantage, though, is that global pointer we're using for the head pointer. I've highlighted it in red here. We're using head as a global variable. Whenever we want to put a node on the list, we're accessing head directly, which means this code would only ever have one list. And for some applications, that may be fine. Maybe you're writing a little program and it's just got one list of things it has to worry about. But if we wanted to really write reusable linked list code, we ought to be able to make as many lists as we want. And this isn't going to do it if this function depends on using one global variable for the head of that list. I guess we could try to make this function smarter by making the list it operates on a parameter. How about if we did this? So here, almost the same function, except I'm not going to depend on head being a global variable. I'll pass that in. Almost all of this is the same. We'll make a new node. We'll fill in its value. We'll take whatever the head pointer used to be, and that's now after the node we just made. And I'll set head to get a copy of the pointer I just made. And then to use this, you'll make a pointer that's the list you want. You'll start it out at null, and then whenever you want to put a new node on your list, you'll just pass in the value you want to add and your pointer. Now, I kind of skipped some parts of my slide as I was talking through this, because I described what it's supposed to do. But that big purple bubble in the middle tells me it doesn't really do that. Here's your problem right here. Head, yeah, it's a pointer. But to put a new node on the list, you have to change the head pointer. And here, well, head is a pointer, but it's just a copy of the pointer that got passed in. Let's say this code down here is in main, just to make it easier to talk about. So in main, you got a variable called mylist. And unless you change that variable, no new node is going to be on the list. When we call this function, we give it our pointer, but it just has a copy, which it has a copy of our pointer, which means inside this function, it allocates a new node, it fills in a value, it makes head point to that. But that's just the head variable inside this function. When this function returns, that head variable is going to go away. It was just a parameter to the function. Meanwhile, the mylist variable up here in main never got changed. We just passed a copy of it to the function. So this code allocates space. It puts a node on a list. It's just the head pointer for that list goes away when this function leaves because it was a parameter to this function, like a local variable. We can fix this. In fact, there are a couple of ways we can fix it. Questions before we start fixing? So at this point, hopefully you feel good about what's wrong with this code.
Dr. Joe, I have a quick question. Is that the new node like add in front of the list or at the back of the list?
You mean the one we're making here?
Yeah, the new node. I mean, whenever like we have the list and then if we create the new node, is that like an add?
Well, the way I think this will answer your question. Let me try. The way we're making the node and the way we're trying to link it in would put it at the front of the list. So if the list already had 20 items on it, if this code worked, all of those 20 items would be after this node, and the new node we just put in would be in front of all those.
All right.
I mean, hopefully that makes sense looking at this code. So you had a list, maybe head pointed to something. Now, whatever it used to point to comes after the node you just made. So that would be out here off the edge of this slide. And then head now points to the new node you just made. But this code doesn't actually work because as soon as you return from that, back here in the caller, their list never got changed. So how could we fix this? We need to make sure that the caller's list gets updated. And one easy way of doing this is just to return the updated pointer. Now, in add value to the list, almost all this is the same, but when it's time to return, I just return a copy of what should be the new head pointer. If you compare this to the previous slide, I don't even bother changing the head variable because it's going to go away as soon as I return from the function. I just return what I was going to set it to. I'm saying to the caller, this is your new head. The function, its return type says, oh, I return a node pointer. That's going to be your new head of the list. And to use this function correctly, you've got to be smart enough to do what I'm showing down here. You call add value, it allocates a node for a value, fills in the value. Anything that was on your list comes after that node, and it returns a new head pointer to you. You just got to be smart enough to copy that into your variable. And this works. It's not my favorite technique for updating a list for two reasons. Any questions before I start complaining about this technique? All right, so this works. Why don't I like it? One reason is it uses the return value of a function. Well, it's there to use, but in Java and in C and in a bunch of other languages, you've only got one return slot from a function. There's only one value you can return. And if we could avoid it, it would be nice to save that return value for something else. Or I guess this forces us to use the return value as a here's your new head pointer. And it'd be nice not to have to do that. The other reason is it's not idiot proof. Here, what if the caller forgot to do this? What if they called our function and they thought it was going to magically update their list and they forgot to assign the return value to their head pointer? Well, their code will compile just fine, but it won't actually update their list. So this is maybe more subject to user error than this. So here's another way we could do it. In C, we've got pointers as a way of passing stuff by reference. The problem we've got, if you let me back up a couple of slides, well, the reason this didn't work, this was the first version we started with, it didn't work because when I change head right here, I'm not really changing the caller's pointer. The caller's got a pointer that's supposed to be their head pointer, but they just give me a copy of it. And when I change that copy right here, their pointer is unchanged. What if they passed their pointer by reference? Then I could change it inside the function and it would actually be their pointer that I'm changing. But to do that, the way we pass things by reference in C, you already know, is by passing the address of that thing. So to do this, down in the caller, I don't want a copy of their pointer. I want to know where it is in memory so I can look at it and change it. So they would have to pass in the address of their pointer. And I put that in red down here. If they're passing the address of a pointer, then I've got to change the type that the function is expecting. Well, now it's expecting the address of a pointer to a node. Well, the type for that is pointer to a node. So in the function, that's what this variable would have to become. I want the address of your head pointer, so I want a pointer to your head pointer to a node. But now that I know the address of their pointer, I can get a copy of it. Here I can say, well, whatever your head pointer used to point to, that's now my next node. I just have to dereference to get what their head pointer was. But using that same dereference operator, I can change their head pointer. They gave me its address. So if I put star head, I'm really modifying their head pointer. Here, I'm showing a picture of how you can think about that. Down in main, they've got a head pointer. They give this function a pointer to that head pointer. When it says dereference here, it's saying, give me the value of your head pointer. And when it's assigning that, it's using that to change the value of the head pointer. This is nice because they can't forget to give me the head pointer. The types wouldn't work if they didn't do that. In fact, they can't even give me the wrong type for this because the compiler wouldn't compile it. And this doesn't use the return slot. I could still use that for something else if I wanted. So here, backing up, here we fixed this by returning the new head pointer. Backing up again, this is the one that didn't work. We fixed it by making this a pass by reference parameter. That just meant we had to pass the address of the head pointer. There's one more way we could fix this. Questions before we look at one more way to fix this? If you're coming from Java, you'd probably say, I never had to worry about this in Java. I never even had to pass a head pointer around. When I wanted to change the head pointer, I just changed it. Probably that's what you remember from Java. And depending upon how you did this in Java, it was probably that way because you probably made an object for your linked list. And if you did that, your object was probably had methods to add nodes to the list, to look at nodes on the list, and it probably had a field for the head pointer. Well, methods in an object can access fields on that object. So here, if we were doing this in Java, we wouldn't have even had to pass this in. We could just access that. If this would be a method, and then the head pointer would just be one of the fields of the object that it's a method on. We can fake that in C. We just need another object to represent the list itself. We've already got an object to represent nodes, or at least a struct to do that. Let's make an object to represent the whole list. That'll be another struct in C. But you can see here I made a struct. I went ahead and type-defed it to the name list because I think of it as representing not just a node, but my whole list. It's only got one thing in it, and that's the head pointer. This object is like a little wrapper around the head pointer. But since I've got an object for the whole list, I've got room for other fields if I wanted them. Like if you wanted a tail pointer for your list to make it easy to put nodes at the end, if you wanted a count of how many nodes are on your list to make it easy to report the length of the list without having to traverse the whole thing, you could just make those additional fields in the struct. So in C, if we wanted to say, oh, we need an object for the whole list, then we could just make another struct for that. That's what I'm doing here, and a lot of our later examples will do this same trick. If we had an object for the whole list, how would that change our code? Well, now if we've got code that wants to use a list, it needs to make one of these structs, and that's what I'm doing down here. Let's pretend this is client code. This is code that's going to use a list. Maybe it's in main, or maybe it's in another function. If it wants to make a list, it needs to make an instance of this list struct we just defined. That's only got one field in it. It's backing up, it's this head pointer that we put in there. And if it wants to start out with an empty list, it needs to make that head pointer have a value of null. It's easy to do that just with an initialization expression. I'm thinking of it as an object, but it's really just a struct in C. So I could just use initialization syntax to say, put a null in that head pointer. So here, main, or whatever the client code is, has an empty list. If I want to make what works kind of like a method for adding something to the list, well, I got to pass in the list it's supposed to add stuff to. So, and it wants to be able to change what's in that list. So I'll just give it a pointer to the list object I just made up here. If you look at the function, now it's expecting what value do you want to add a list to a list? Oh, and give me the list you want me to modify. It's expecting a pointer to the list. Most of the rest of this code is the same. It mallocs space for a node. It fills in the value. And then these last two lines, it links it into whatever list you gave me. List is a pointer to a little struct, backing up a struct that looks like what we defined here. So it's a pointer to that struct. If I want to say, well, whatever was your first node on the list, that comes after the node I just made. So n next now points to whatever your head pointer used to point to. And your head pointer is now pointing to the new node I just made. I got a picture over here that tries to show how you can think about this. In main, or whoever the caller is, you make one of these list objects. It's got a head pointer, but like I tried to say before, it's got plenty of room for additional pointers if you want them. Whenever you call this function to add a node to a list, you have to give it a pointer to the list you just made. Questions before I try to move on? I started talking about this kind of like we're writing objects. And this is how you would normally write code in C that works with objects, or that works with things like objects from Java. It's normal in C to write a bunch of functions that might work on a struct. Maybe they modify its fields, or maybe they use its fields somehow. And if you don't want to copy that struct every time you do that, whenever you call those functions, you just pass them a pointer to the struct they're supposed to work with. That's kind of like calling a method, except when you call an instance method, it automatically has access to the object that it's called on. In C, well, C doesn't really know about object orientation. So when you call a function that works kind of like a method and an object, you have to give it a pointer to the object it's supposed to work on. This is, you could think of this as how we could fake object orientation in C. If we wanted an object, that's just a struct. If we want a method, or something that's like a method on that object, we can just make a function that takes a pointer to that object, typically as its first parameter, maybe along with a bunch of other parameters for that function. And then whenever we want to call that method, we call that function, and we pass in a pointer to the object that it's supposed to work on. If you look inside Java, if you look at what's going on in the Java virtual machine, it is secretly doing the same thing. When you call a method on an object, you don't have to write code for it. But if you look at what happens inside the JVM, it pushes the object that you're calling that method on as a first parameter to that function, even though you don't write the code to pass it in internally. An object is automatically getting passed to a method when you call an instance method on an object. Sorry, that was a lot of object description there. Questions before I try to move on? All right, if you make linked lists the way I just talked about, then every time you put a new node on the list, you've mallocked a little bit of memory. And you've got to have a plan for freeing that memory, or it's going to look like a big memory leak, or really a lot of memory leaked, one for each node. So typically, if you make a linked list like this, you're going to free all of the memory for it, and that means freeing every one of its nodes. Freeing a list is kind of like traversing a list. You just have to go through all the nodes and free the memory for every one of them. So here's a for loop, just like we wrote before. This is the same for loop that goes through every node on the list. But instead of printing out what's in that node, I'll just free the memory for that node. And this would, well, except for this little bubble over here, this would walk through all the nodes on the list, freeing each of them. But this isn't really the right way to do it. And I've tried to illustrate this in the picture at the bottom. The problem with this technique is, imagine you start iterating over the nodes of the list. So you got a head pointer that points to the first node. Each node points to the one after it. You're going to make a variable n that's going to start out pointing to that first node. Inside this loop, you're going to free the memory for whatever n points to. That's like this picture. You gave this memory back to the heap. But then what do you do next? Well, this code says, all right, it's time to free the next node. So let's go look at the next pointer inside the node we're on to go to the next node. Problem is, that's the node you just freed. This little bit of code is accessing the next pointer out of the node that you just told malloc you don't need anymore. So that's not really a safe way to free a linked list, because you're actually, I would say this is a dangling pointer problem. You're accessing part of memory that you just freed. So we can write code that works. We just can't, we have to write it without accidentally accessing memory that we're not permitted to use anymore. This loop won't, I mean, technically it won't work because you're using memory that you just freed, but this would work. Here, I fix this problem by looking at the next pointer and getting a copy of it before I free the node. And then I use that copy after I free the node. I changed the loop a little bit. Let me tell you how you can think about it the way I've written it. And there are other ways to write equivalent code. This isn't the only way to do it. I'm going to think of this as over and over removing the first node from a list until there's no first node. That's the condition on my loop. If head is a pointer to the first node, then as long as head is non-null, there's a node on the list, at least one node on the list. So inside each iteration, I'm going to remove just the first node, and I'll make head point to whatever remains on the list. I'm about to free a node, but even after I free it, I still need to know what the node that came after it was. So I'll take a picture of that. I think of this line as saying, well, look at whatever the second node on the list was, or really look at whatever the next pointer out of the first node points to, get a copy of that. Then you can free that node, and then whatever came after it, that's your new head node. If it was pointing to another node, now head points to that other node. If it was null, let's say the list was almost empty and there was only one node left. Well, then when you do this, next is going to be the null pointer. When you do this, when you say, all right, let's take next, now that's my new head pointer. Well, if there was no other node on the list, now head is the null pointer, and that'll make you bail out of this loop. But until the list is empty, you're going to keep iterating, removing nodes from the list until you've removed that last node. Questions? So we've learned how to make linked structures, at least one of them. We've learned how a couple of different ways of managing lists and making it easy to add nodes to a list. We've talked about how to free a list, and very early we talked about how to traverse a linked list. Questions? One thing, and we'll visit this today and we'll revisit it a little bit later. But like we saw a couple of examples ago, having access to pointers in C gives us a lot of clever ways of manipulating data structures. Having a pointer to an int makes it so that you can look at what's in that int or change what's in that int. For a linked structure, working with the pointers in that structure, making them point to different things, making them point to null, that's how you change what's in the linked structure. Well, if it's easy to change things via pointers to them, then if you're willing to keep up with pointers to the pointers in your linked structure, that can give you an awfully simple way, or at least an awfully short way of changing what's in a linked list. If you let me back up several slides, that's really what we were doing here. This was our second example of how you could update a linked list by passing a pointer to its head pointer to a function. If I know where your head pointer is in memory, I can look at it or change it. We could use that same trick to make it easy to modify what's on a linked list. And that's what we're going to talk about doing next. We'll look at one example of that, and we'll revisit this again later in the semester once we've seen a few other tricks, and we'll look at some of the syntax in more detail. But we'll see how by keeping up with pointers to the links in a linked list, that can make it easier to update, or can let us update what's in the linked list with even shorter code. We're going to use the same representation we've been using for a linked list. We'll pretend we have a node, same definition we've been using before, like the picture on the left. It's got a value field and an X pointer. We've type defed it to just the word node to make it easy to make instances of this. And kind of like we did before, we'll pretend we have a little struct for the whole list itself. It just contains a head pointer, but we could put other stuff in the struct if we needed to. Let's pretend we want to write a piece of code to remove a value from this linked list. And we haven't done that yet. We wrote code to add values to the front of the list. We wrote code to free the memory for the whole list, but what if you just want to remove one node? Well, I guess if you're coming from Java, the standard way of doing this is to treat the first node as a special case. And that's what this version of the function does. We're going to define a function called remove value. You give it the value you want to look for. So if you want to remove the value 42, you pass that in here. As the first parameter, you give me a pointer to the list you want to remove it from. And just like on the previous slide back here, we're pretending you have a struct for the whole list. It's really just a wrapper around the head pointer for now. You pass in a pointer to that struct as the first parameter. So you're asking, go through this list, and if you can find a copy of that value, remove it. The return value from the function is success or fail. It returns true if it does remove the value you ask for. It returns false if it can't, if the value isn't on the list. I said this a moment ago, but if you're coming from Java, a normal way of writing this code is to treat the first node as a special case. Like let's say you ask me to, let's say this is my linked list at the bottom, and you ask me to remove 103. Well, it's the first node on my list, so to remove it, I have to, well, in C, I'm going to have to free the memory for that node, and I'm going to have to make the head pointer point past that node. So it's got to point, instead of pointing to the node with the 103, I've got to modify the head pointer to point to this node with a 9 in it. I say that's a special case because any other node I remove by changing the pointer in the node before it. So if I had to remove this 9, well, I have to change what's in this 103 node. If I had to remove this 42, I have to change what's in this 9 node. But for a node like this 103, there isn't a node before it. To remove it, I got to change the head pointer. So that's what this if does. It says, if you ask me to remove a value first, let's see if it's the first node on the list. This condition looks kind of ugly, but let me talk you through it. And I claim it makes a lot of sense. If you gave me the value 103 to remove, first, I better make sure there's a head node, because I can't look at the value of a head node if head is null. That would give, that be accessing memory I'm not permitted to access if I tried to dereference a null pointer. So first, this part of the condition says, is there a head node? Take list, get its head field, backing up a slide, that's just getting this field right here. And I'm asking, is that non-null? Does that point to something? So you can read this as long as the head pointer points to something, so there is a first node on the list, and it has the value I'm looking for. So here I'm just saying, all right, the head pointer points to something. Otherwise, I wouldn't have even gotten to the second part of this condition. So if the head pointer points to something and that head pointer points to a node where its value field is the value you want to remove, then I want to remove the first node. So these two lines unlink it from the list. Well, really this line unlinks it from the list. First, I make a copy of the head pointer because I need to free it at the end. So I make a copy of the head pointer and then I skip over it in the list. Take whatever, let me read this line to you. Take the head pointer out of list, get its next field, and copy that into the head pointer. So that's like taking this pointer that points to the 9 node and copying that pointer into the head pointer. Now head points to the 9, to the node with the 9 in it. All right, so that line unlinks the node from the list. If I was in Java, I'd be almost done, but in C, I've got to worry about freeing that node. If I'm allocated space for it, someone better free it, or it's going to look like a memory leak. So fortunately, I made a copy of the pointer to the node I just removed. So I free that memory, and then I return true. This takes care of the special case of removing of the first node on the list. And again, this says, if the value you ask me to remove is the first node, here's what I've got to do to remove it. This is the rest of this function, and that takes care of the general case. Otherwise, if the node if the node I'm supposed to remove isn't the first one, then I need to remove it by finding its predecessor. Questions, especially questions about what we just did here before we move on? All right, so let's say I have to remove that 9 or that 42 on the list. I've got to go find the node that comes before it. Like if I had to remove the 9, I've got to find this node. I don't really care about the 103, but it's the node that has a next pointer that points to the 9. If I've got to remove the 42, I've got to find a node that has a next pointer that points to the node with 42. That's what this loop does. I'm looking for the predecessor. I know I don't have to remove the first node, so I'll start out with that as my predecessor, and I'll go look for a node that comes, or I'll look for a predecessor that comes before the value you ask me to remove. That's what the condition on this loop says. You can think of it as saying, well, keep going. Keep moving pred ahead down the list, as long as, well, there is a node that comes after it. Pred has a next pointer that's non-null. So there is, you can think of that as saying, as long as there's a node that comes after this, and it's not the value you're looking for. Pred has a node that comes after it, and the value in that node is different from the value you're looking for, then just keep moving down the list. That's what this says. It's the same same kind of update we had in our linked list traversal before. Take whatever the next node was, whatever the next pointer out of pred was, that's your new pred. So when I do this, like let's take this first case here. If pred was pointing at this 103, this, we'll go get the next field out of pred, is saying we'll go get a copy of this pointer and assign that to pred. Now pred points to this node with a 9 in it. If you did that again, same expression, then pred would point to the node with 43 in it. So this is moving pred down the list. So this as a whole says, well, go find a node that comes before the node you're looking for. This loop is going to stop if either you get to the last node on the list or you find the value you're looking for. That's what this if checks for. Well, you bailed out of this while loop because either you found the last node on the list, so it wasn't the predecessor to anything, or you found the value you're looking for. If there's a node that comes after pred, then you must have bailed out of this loop because you found the value you were looking for. So that's what we test here. If there's a next node after pred, then that must be the node I want to remove. So I remove it. This code, backing up, is almost the same as this code, but instead of changing the head pointer, I'm changing the next pointer out of the node that I'm looking at, out of the predecessor node. I get a copy of the node I'm removing because I'm going to need to free it before I'm done. I unlink it from the list. Let's pretend like my picture that it's this 9 we're going to remove. This says, well, go take whatever came after the 9 node. Take pred, get its next pointer, get the next pointer in whatever that points to. That's what this says. So that's this pointer, the one that points to the 42. Take that and make the next pointer out of the predecessor node have a copy of that. So that takes this pointer to the 42 node and it copies it into this pointer, this next pointer in the 103 node. I don't have a picture for this, or I can't actually draw on my slides here, but that would make this pointer point, since I copied this pointer into this next one, that would make it point over the 9 node and point to this 42 node. So that's why I say this unlinks the node from the list. It skips over it. And then I don't want to leak the memory for this node that I just removed, so I free that. And then I return true because I successfully removed a node. Otherwise, I never found the value you asked me to remove, so I return false. So these two slides show what it would normally take to remove a node from the linked list. They're longer than they should be or longer than they have to be because they treat the first node as a special case. But if we're willing to keep up with pointers to the pointers in our list, we can cut this code in half, roughly. We can shrink the code significantly by getting around that problem of having to treat the first node as a special case. And that's what we're going to do next. Here's some code that doesn't work, but it almost works. And it's going to be easy to turn it into code that does work. Before we do that, questions about, so this is our previous version. This is the 2-slide code that it takes to remove a node from a linked list. Pretty analogous to what you probably did in Java with linked list. It's just in Java, probably all of these arrows were dots. And you probably didn't really need this list object because you just used whatever object your method was defined in for that. Questions? All right, people are still here. All right, moving on. So here's the idea that we're going to implement. Instead of, wouldn't it be easy? Wouldn't it be nice if I could just go find the node I want to remove and remove it? I could have a pointer to target. That'd be the node I want to remove. And I could just go look for a node that has the value I want to remove. That's what this code does. Target starts out with a copy of the head pointer. And as long as I have a target node and its value isn't what I'm looking for, I just keep moving down the list. Target gets whatever came after the current target node. So I think of this while loop as marching target down the list until I find the value I want to remove. Let's say I want to remove this node with a 9 in it. Well, when I find the node with a 9 in it, target's going to be pointing at that node. So if I find the value I'm looking at, well, I stopped before I hit the end of the list, so target's non-null. All I need to do is remove it. So let me talk you through it real fast because this is the part that isn't going to work. It's the part that we need to fix. But let me tell you what we're trying to do here, and then I'll explain why it doesn't work, although it's probably obvious why it doesn't work. Here, I'm about to remove the target node. So I found the node I want to remove. Target points to this node with a 9 in it. I'm going to need to free that. So I take a copy of the target pointer. I unlink it from the list. So whatever came after target, that's what target needs to point to now. I free the node I just removed and I return true because I successfully removed it. It's really this line right here that doesn't work. Problem is this line doesn't actually unlink the target node from the list. My picture shows what it does. Just making target point to the node after it doesn't change the linking structure of the list. Target's just a local variable. Making it point to the node after the one you want to remove doesn't change where the pointers on the list point. To remove it, I need to remove this node with the 9 in it. I need to change this pointer, not the target pointer. I need to change the pointer that points to that node. In fact, That's true for any node, including the first one. If you want to remove this 42, that's the pointer you need to change. If you want to remove this 9, then this is the pointer you need to change. It's the next pointer in a node. If you want to remove this 103, then this head pointer is the one you want to change. Well, head pointer isn't a pointer in a node, it's at the front of my list, but it's still a pointer to a node. Instead of keeping up with the predecessor node to remove a node, how about if you keep up with the pointer the pointer you have to change in order to remove a particular node? And let me talk through that again real fast. To remove this 42, well, that's the pointer to a node you need to change. To remove this 9, that's the pointer to a node that you need to change. To remove this 103, that's the pointer to a node you need to change. So let's make a loop that keeps up not with the node that contains a pointer, because that wouldn't work for the first node on the list, but the pointer that points to that node. It'll be sorry, I don't have to back up to a slide. It'll be almost the same code as what we've got here. We're just going to change the job target does. Instead of pointing directly to the node we might need to remove, it'll point to the pointer to that node. I got a picture for this. And that's what's on our next slide. So target, when I'm looking at this node with the 103, I'm not going to have target pointing straight to the node with the 103. It'll point to the pointer to that node. Or think of it this way. It'll point to the pointer you have to change to remove that node. It'll start out pointing to the head pointer, and then as I march it down the list looking for the node I want to remove, well, then it'll move ahead to point to the next pointer inside the first node. And if I kept moving it down the list, then it would point to the next pointer inside the node with the 9 in it, and then the next pointer inside the node with the 42 in it. This picture doesn't show that because here I'm pretending, let's pretend the 9 is what you want to remove. Well, if you've got a pointer to the next pointer that points to that node with the 9 in it, you can tell, oh, I found the node with the 9 in it. My target pointer points to a pointer that points to a node that has a 9 in it. And if you know the address of this pointer, you can change where that pointer points. You can make it skip past that node with the 9 in it, effectively removing it from the list. So backing up 2 slides, we're going to write code that looks almost exactly like this, except target's job is going to change a little bit. And I already said this, so I'll say it quickly this time. Instead of pointing at the node that you may or may not remove based on its value, it'll point at the pointer that goes to that node. It'll start out pointing to the head pointer, and then as we move it down the list, it'll point to the next pointers inside nodes until either we get to the end of the list and we didn't find what we were looking for, or we find a pointer that points to the node that we're looking for. So this picture shows it'll start out pointing to the head pointer, and then we'll move it ahead pointing to the next pointer inside nodes until, again, either we find what we're looking for or we fall off the end of the list. This code is almost the same as what we had before, but like I promised, target isn't pointing straight at a node, it's pointing at a pointer to a node. So its type had to change. Target is now a pointer to one of those node pointers. And like I said, it's going to start out pointing to the head pointer. I take the address of the head pointer, and that's my first value for target. And then I need to go look for the node I might want to remove. And I'm either going to find it or I'm going to fall off the end of the list. I've reached the end of the list when the pointer that target points to is a null pointer. So I want to keep on going as long as target isn't pointing to a null pointer. It points to a pointer. It's just as long as that pointer points to a node, I want to keep going. And as long as the value in that node isn't the value I'm looking for, I want to keep going. So this part says, well, the target node, is it a non-null? And its value, is it different from the value I'm looking at? And as long as as long as there's still nodes on the list and I haven't found the value I'm looking for, I'm going to move ahead. Target points to a node. Well, technically the right way to say that is it points to a pointer to a node. So go get the pointer it points to, get the next field in that node. The address of that next field is my new target. So and I probably should have said this at the start. As I'm moving down the list, that's what I need to do to update target, to move it ahead to the next pointer inside the next node. And then I'll bail out of this loop either because I hit a null pointer or I found the value I'm looking for. If I didn't hit a null pointer, then I must have found the value I'm looking for. So I unlink that node from the list. This code is almost the same. I have to back up 4 slides to show you this. It's almost the same as this code. It's just target isn't a pointer to a node. It's a pointer to a pointer to a node. So if I want to take a picture of the node I'm about to remove, I need to dereference target. And that lets me get a copy of a pointer to a node, a copy that I'm going to free later. And then this was the line that didn't work before. This was the one I complained about, that just changing the value of target doesn't change the linking structure of our list. But now I'm not changing the value of target. I'm changing the pointer it points to. I'm assigning to whatever target points to. So if target points to this next pointer, assigning to that will change this next pointer. I'm going to use it to make it point past the node I want to remove. Well, take whatever node target points to, get its next pointer, and then assign that to whatever target points to. That'll change this red pointer to get a copy of whatever this next field was, effectively making that red pointer point straight to the 42 node, because it just got a copy of this next pointer. This unlinks that 9, well, if 9 is the value you're looking for, and that's what my picture shows. This unlinks it from the list, but so that we don't leak memory, we free that memory, and then we return true because we successfully found the value we were looking for. Otherwise, we return false. Well, I probably oversold this a little bit. I said we can cut your nodes, or sorry, we can cut your code in half. Now, this is probably a little worse than half, but here a little more than half. This is what it takes to do a linked list removal by keeping up with the pointers in the list rather than pointers straight to the nodes in the list. And backing up a few slides, here's what we started with. So when we had to handle the first node on the list as a special case, we needed this code plus this code. Well, now we got it down to pretty much just the size of this code. This saves us a little bit. Sorry, this saves us a little bit on a simple linked structure like a linked list. Later, we'll use the same trick for writing some code that does binary trees. And their trees are even a little trickier because they have a left and a right pointer out of each node. But using similar techniques, we can write the same code to handle either the left pointer or the right pointer. That's going to let us write some awfully short code to work with trees using, again, the same technique. But we'll save that for another day. And we are caught up. That's all I planned to talk about for today. I'll keep recording for a moment in case people have questions they want to get recorded. And then I'll stop recording and I'll hang around a little bit after that. Any questions while we're still officially here?
Yes, sir. I do have questions about adding to the list.
Adding to the list?
Yes, sir.
All right. I just asked because just to know where to go in the slides. Yeah, so here was our first code to add something to a list. Go ahead.
So, I mean, I understand that, like, you say that like adding to the list will add to like front of the list. But is there a way that like we can, add in the middle of the list or like at the end of the list in the C, or no?
Oh, absolutely you can. I just picked this because it's easier. But yeah, you could definitely add anywhere in the list. It's just adding a node to the front is easy because you just have to change the head pointer to point to that node.
Yeah.
But the trick that we're using to do removal is kind of like what you might do, or what you could do to add anywhere in the list. Like here, we're removing a node, so we either have to remove it from the front or we have to change its predecessor node. Same would apply if you wanted to add somewhere in the list. You might say, well, if I want to add to the front, I need to change the head pointer. If I want to add somewhere in the middle, I have to find the predecessor node. So you could turn this into code that added instead of removed, and it would have similar things to deal with.
So my question is like, if we try to like add in the like somewhere in the middle of the list, do we have to like, like the current node to be starting from the head, or like it has to be, and then like we can keep on traversing until to find the node that we need to, the place that we need to add?
Yeah, I don't know if this is an answer to your question, but let me give it a try and you can correct me if I answered the wrong thing. If you want to add, like, let's say you want to keep your list sorted. So when you add a value, you need to worry about, well, what are the other values in the list? Well, then you might want to go find the first value that's bigger than what you want to insert. And then you want to put your new value in front of that. So there, kind of the right way to do that might be to go find where you need to insert it in the list. That would take a traversal of the list, and then allocate space for the node and insert it there. And sometimes that makes sense for linked lists, but more often you use linked lists because you need to be able to efficiently insert at the front and the back of the list. It would depend on your application, but linked lists are really good at that. So we've looked at code that makes it efficient to insert at the front. We could also write code that makes it efficient to insert at the back. If you knew you only had to insert at the back, then you could just keep a pointer to the last node on the list. And that's usually called a tail pointer on the list. And then whenever you put a node in that, or put a node at the end of the list, that's your new tail pointer. And then you wouldn't, in that case, you wouldn't have to go hunt for the place to insert if you knew it was always at the end of the list. Other questions?
That's fine.
I said I would stop recording after a while, so if that's all the questions that people want recorded, I'll go ahead and stop. But I'll hang around